Hello grade 11 mindsetters, welcome to today's physical sciences show. Today we have a special revision lesson on mole calculations. We have selected highlights from lessons shown earlier in the term to help you revise. Please post your comments and questions on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision. You can also download the notes for today's show from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
Right, now, when we talk of moles, and especially when we're talking around gases, okay, what is a mole? A mole is just an amount of matter. It's this substance, it's this amount of matter that constitute a specific value, and that amount we can call it a mole. And remember that if we have this, the Avogadro's number of particles of anything, Avogadro's number, all right, then we have a mole. Those particles should be 6.02 by 10 to the 23 particles, whether we've got molecules of a gas or whatever. If it amounts to that number, we've got a mole. So it is just an amount of matter. Mass, when we deal with masses, when we are given mass from a particular situation and we are to find moles from mass, if we are to find moles, we use this very important formula. That number of moles is equal to given mass divided by the molar mass of the substance. Okay, that M there is molar mass. We know that from here, what small n represents is the number of moles, which is what we will be looking for. And what small m represents, it's the mass of the sample. In other words, if you are given a substance in mass, grams, kilograms, whatsoever, for you to get the number of moles, you use this formula. So M is the given mass of that sample or that substance. And capital letter M with a small letter, with a subscript M sometimes, or just capital letter M, that is what we call the molar mass. It's the molar mass of that substance. And this you get by working it out from the periodic table, okay? And its unit of measurement, it's grams per mole. Right, so we know that. Next, when we're talking moles, and this time talking about gases specifically, we know that from gases, when we talk of volume, there is a volume that is occupied by 1 mole of a gas at standard temperature and pressure, which is this here. And that volume is 22.4 cubic decimeters. Let me just explain this a little bit, because I think some people sort of get it confused with it. Look, what we are saying with standard values, the volume that can be occupied by 1 mole of a gas. If I've got 1 mole of a gas, say nitrogen dioxide, 1 mole of nitrogen dioxide at STP will occupy 22.4 cubic decimeters of volume. So if I've got more than that, the volume will be slightly more according to the amount of gas that I have. If I have got a little bit less, the volume will also be a little bit less, okay, less than 1 mole. Why? Because only 1 mole will occupy 22.4. If it's less, then there shall be a lesser volume. Okay, good. So if we're talking about that situation, it would mean that this number of moles, N, the very same N, will be given by the given volume, okay, divided by the molar volume. And what do we mean by the molar volume? We mean that 22.4 cubic decimeters. Again, N is the number of moles, V is the given volume of the sample of a gas, and Vm, or V subscript M, it's our molar volume, which is 22.4 cubic decimeters per mole. Okay. Now, if you were to convert then, converting from, say, because we know that we don't work in cubic centimeters, but usually our volume is given in cubic centimeters, okay? And sometimes in cubic meters. And sometimes, of course, we are required to move from these values to cubic meters. So how do we convert? If I am in cubic decimeters, 1 cubic decimeter equals 1,000 cubic centimeters. And 1 cubic meter is 1,000 cubic decimeters in that way. So that would mean that if I am to move from cubic centimeters to cubic meters, then I'll have to multiply by a factor of 10, to the power minus 6. In other words, dividing by 1,000,000. Okay, so that's what it means there. In a balanced chemical equation, the number in front of the chemical symbols will always describe the mole ratio of the reactants and products. Okay? Simple. If you have this example here, for example, if I've got H2 gas reacting with O2 gas, giving me H2O gas. All right? This is vapor. If I balance this equation here, I'll put a 2 there, and that's a 4, so I will therefore have a 2 here. What we are talking about is this. These numbers are the ratios in which the reactants here are combining to give us the products here. Okay. Okay, and the ratio of hydrogen, for example, to water, it's always 2 is to 2, therefore it's 1 is to 1. But for oxygen here, the ratio will be 1 is to 2, all right? So it will be 1 is to 2. That is the ratio that we're talking about when we're talking about the number in front of every substance there, giving us the ratio in which products or in which reactants and products are actually related to each other. Okay, now, when we talk of concentration, what is this? We can have moles in solution, okay? So in this time we take moles of substances, we dissolve them in solution. When we do that, we create or we form something called a concentration. The concentration of a solution refers to the number of moles of dissolved substance per unit volume of that solution, which is of course in cubic decimeters. A solution of known concentration, we call that a standard solution. The concentration of a solution is calculated using the following formula. Okay, now that becomes very important. So concentration equals number of moles divided by the volume in which this number of moles or this amount of a substance has been dissolved. Okay, so we should know that our C there stands for concentration, and it is measured in mole per cubic decimeters, small letter n, number of moles, and V there, the volume in which this number of moles have been dissolved. Okay, so that is what it is all about there. Okay, so you would see here, if I were to look, we're talking a lot around moles here. Let me just use this part here to link up something. Mole. We saw that from the mass, given mass, okay, number of moles will be equal to given mass over molar volume, okay, for the molar volume. Okay, so there we go. But the same mole, we also saw that if I'm talking about gases at STP, the number of moles can be found by looking at the given volume divided by the molar volume, which is, of course, always, remember, this is always 22,4 moles per cubic decimeter. Okay, moles per cubic decimeter. Okay, so that is the molar volume. But then the same mole, okay, the same mole, when we're talking about concentrations, what happens? We see that concentration is number of moles over volume. Very important. But then if I were to just talk, talking about number of moles from this equation here, number of moles will be equal to concentration times the volume. This is when we're talking solutions. So all this becomes very important for you to note because they are related. I mean, if we're talking about an amount of a substance, a specific substance, whether it's a gas or whether it's in a solid substance, whether it's a liquid substance, if we're talking number of moles, that N applies here, and it will also apply when we're talking concentration of that substance. It will apply when we're talking the mass of that substance. It may not apply if we're talking about gases, if it can never, convert into being a gas. But if we heat it, to high a temperature enough, we know that it can vaporize. Okay, so all these apply. In other words, when you're solving problems that involve moles, think about any possible way of working out those solutions. Okay, limiting and excess reagent. What is a limiting reactant or reagent? A limiting reagent is completely used up in a chemical reaction. Nothing of this substance remains after the completion of the reaction. So when we talk of a limiting reagent, we're talking about that substance that will be completely changed in that chemical reaction. But the excess one is the one that will remain. We would still have some quantities of this excess reagent because now it has got nothing more to react with, because now the limiting reagent has completely been used up. That's what it means. So when we talk this excess reagent, this one is not completely used up in a chemical reaction. Okay, and when we come to the yield is the amount of product formed. Okay, if we want to know the percentage yield, we look at the actual yield divided by the theoretical yield multiplied by 100, and therefore we find the percentage yield. Now, quickly, what is this actual yield? Actual yield means when a reaction takes place, all right, we know at the end that we have produced so much. Say nitrogen is reacting with oxygen to form nitrogen dioxide. The yield is how much of the product we are having. When we balance that chemical equation, we can calculate how much of the product we're going to have if we are given the quantities that are reacting. But that is called the theoretical yield. What we calculate making use of the chemical equation is called the theoretical yield. But if the reaction takes place and we find out that instead of what we calculated to be the quantity of the product that should be formed, according to how the substances are combining in their ratios, we find that less of it has been produced. That less of it that has been produced, which is actual, is what we are seeing. We put it up here. It is the actual yield. We divide that by our theoretical yield, which is our calculation. And we multiply that by 100%, and we have now found what we call the percentage yield. Okay, We're going to do examples, of course, later on to show you more on how this is done. Percentage composition. Here, by percentage composition, this is something that tells us about the amount in percentage of an element or a compound in a substance. For example, the percentage composition of sulfuric acid. Okay, so you've got sulfur, you've got, in sulfuric acid, you know you've got this. You've got hydrogen, you've got sulfur, you've got oxygen. So we find how much of each of these elements is in a molecule of sulfuric acid. First, you find the molecular formula of, the molecular mass, the molar mass of sulfuric acid. How do we do that? This is sulfuric acid. 2 to 1 for hydrogen, 32 for sulfur, 4 into 16 for oxygen. And that works out to 98 grams per mole. All right? Find the percentage of each of this. For hydrogen, we have got 2 out of that 98 times 100. That is the percentage. For sulfur, we have got 32 over, or out of the 98 times 100, it's 32.65. And for oxygen, we have got 64 of 98 times 100. And then we find that the percentage is 65. Empirical and molecular formula. Empirical formula is the simplest ratio of elements in a compound. Percentage composition of a substance by mass is used to determine what we call empirical formula. For example, let's look at this one here. A substance contains 36.5% sodium, 25.4% sulfur, and 38.1% oxygen by mass. If it is by mass, so we can convert these percentages into grams. We can say this is mass. Okay, and when we do that, we say that let's find out, because our compound contains sodium, sulfur, and oxygen, but we don't know what are these values here. So we just say X, Y, Z. So for sodium, we say, okay, it's 36.5%. So it's 36.5 grams divided by the molar mass of sodium, 23. It gives us 1.59. We do the same for sulfur. It's 25.4 divided by 32. It gives us 0.79. For oxygen, we do the same. It's 38.1 divided by 6. It gives us 2.38. And the ratio is therefore 1.59. This is sodium. And then 0.79, this is sulfur. 2.38, this is oxygen. Okay. Then at this point, we take the smallest ratio here, which in this case will be that one. Okay. And we divide through all of this to simplify the ratio. When we do that, we find that 0.79 goes 2 times to 1.59 for sodium. It goes once to itself for sulfur, and it goes 3 times to 2.38, this one, for oxygen. Remember, this is sodium, sulfur, oxygen. This means that the empirical formula for this substance containing sodium, sulfur, and oxygen will be this one here, Na2, this one. And then sulfur, all right, it's 1, that one. So there's 1 there. And oxygen, it's 3, this one here. So that Na2SO3 is the empirical formula. This is the empirical formula as we found it there. Okay. Right, so, and lastly, if we are to find what we call percentage purity, okay, this percentage purity is calculated using the mass of the compound divided by the mass of the sample.
Okay, guys, I hope you're enjoying this revision session. If you need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. Now it's time to take a quick break, but don't go away. We'll be right back. Welcome back, guys. We have some great news to pass on to you. We will be bringing you winter school from the 30th of June till the 20th of July, starting at 10 a.m. every weekday. To get the full schedule, visit our website, learn.mindset.co.za, and look for the winter school link. Join us. It's going to be a lot of fun. But now it's time to get back to the lesson.
Question number 1 here says a certain mass of nitrogen gas, or nitrogen dioxide gas actually, so we're talking NO2. This gas occupies a volume of 350 cubic centimeters at STP. Calculate the mass of the nitrogen dioxide gas that is present there. Now we are given this here, we're given the volume that is occupied by the gas. All right, we have the volume. We are also given the type of the gas. We are also told that this gas is at STP. Okay, now if it is at STP, what do we know? All right, what do we know? What we know is that 1 mole of this gas will occupy 22.4 cubic decimeters of volume. So the question is, how many moles of this gas will be occupying this volume here of 350 cubic centimeters? And of course, we will need to convert it into cubic decimeters. So let's just do that immediately. So this is equal to 0.35 cubic decimeters. So that's when you have converted cubic centimeters to cubic decimeters by dividing by 1,000 here, so that you get to the cubic decimeters. Okay. Now, how does this help us? We are to find the mass of nitrogen dioxide in that container. But then how do we get there? We need to start by finding the number of moles in that volume. And the number of moles in that volume will be, all right, so because we know the molar volume, okay, we know the molar volume, the volume occupied by 1 mole of that, and we know the volume that is occupied, the exact volume occupied by this gas. We can then say number of moles of the gas available. Okay, you can say N will be found by given volume divided by the molar volume. Now, given volume is 0.35 divided by the molar volume is 22.4 moles per cubic decimeter. Okay, now, so what will this work out to be? Right, you can use your calculator quickly. Right, so let's go to the calculator. It's 0.25 or 0.35. Oh, delete. 0.35 divided by 22.4. 22.4. All right, so what will this work out to be? Right, so that is 0.016 moles. Okay, so 0.016 moles. Okay, all right, so if this is 0, if we've got 0.06 moles of what? Remember, of nitrogen dioxide. The question wants us to find the mass of nitrogen dioxide in that container. Now, This means that we can actually say, because from this formula, number of moles, oh, it's going on with this thing here, right? Number of moles, N, is also given by mass divided by molar mass. Okay, now the question is now, do we have the molar mass? We don't have the molar mass, we have to work it out. Okay, so there should be a way of us finding out what that molar mass is. And how do we do it? This is the molar mass of nitrogen dioxide. So molar mass of nitrogen dioxide, we can find it out, MnO2, molar mass of nitrogen dioxide. How do we do that? We go to the periodic table. For nitrogen, let's check it. There is nitrogen, 14, okay? So we say 14 there. For oxygen, just next to it, 16, okay? So we come back to our calculation. Okay, let's come back to our calculation. We found that for oxygen, for nitrogen, we're talking 14. For oxygen, it's 16, but we don't have just one of the oxygen atoms. We've got two, so it will be 2 into 16. We work this out. This becomes 14 plus 32, all right? And therefore, this is 46 grams per mole. This is the molar mass of what? Of nitrogen dioxide. Okay, so with the molar mass of nitrogen dioxide, we can then find what the mass is, because we know the number of moles. Here is the number of moles, 0.016 moles. Okay, and we use, of course, that formula. Number of moles is given mass over molar mass. 0.016. I think I got that right. Let me be sure. Yes, number of moles is 0.016 equals. Mass is what we are looking for. We have calculated for the molar mass, and the molar mass is 46 grams per mole. Therefore, your mass is 0.016 times 46. So, all right. So we can go back to the calculator here and work it out. Okay, so we can actually, because this is the number of moles, we can just multiply that by 46 and we get exactly what the answer is. So here we've got 0.72 grams, 0.72 grams. So the mass is 0.72 grams, 0.72 grams. So there is that amount of mass in that volume, okay, at standard temperature and pressure, of course. So what is very important here is to see how you alternate between these several equations that you use to calculate for number of moles, and how you use them in such a way that you solve the problems that are being asked from you. So I think you have seen that. Let's move on to the next one. Okay. The next one says 5 grams of potassium hydroxide. So this is potassium hydroxide, KOH. And of course, this is a base. Okay, it's a hydroxide. This is dissolved in water to make up a volume of 500 cubic centimeters. Determine the concentration of the solution. Okay, now this should be easier to work out. But then let me just take it slower, quickly, and let me take it slower with you, and then I will look at how quickly you can work on it without taking the long way. Let's have a look at it. You've got mass given to you. It's 5 grams. You have got the volume that the solution should actually make. It's 500 cubic centimeters. We work in cubic decimeters, so I can actually convert it immediately to cubic decimeters, which is 0.5 cubic decimeters. All right. Okay. So now I have to find concentration. And how do we get concentration? Concentration is number of moles over volume. So I need to get the number of moles because volume is given to me. The substance is given to me in grams, which is mass. So I need to work out these grams into getting the number of moles. How do I do that? For me to do that, because I've got a substance and a mass of a substance and its molar mass, I can use this formula here. Can use this formula here. All right. Number of moles, it's given mass over molar mass. All right. Now, the molar mass I need to work out. It is a molar mass of potassium hydroxide. Molar mass of potassium hydroxide, what do I have? We go to our periodic table again. For potassium, where it's K, there is K. I've got 39. For oxygen, once again, I've got 16. For hydrogen, there it is. I've got 1. So I can substitute into my molecular formula there and work out what the answer is going to be as being the molar mass of potassium hydroxide. So K is 39 plus oxygen 16 plus hydrogen 1. This is 56. Okay, 56 grams per mole. This is the molar mass of what? Of potassium hydroxide. Okay, so I can then find out what the number of moles is because I'm told or I'm given the mass to be 5 grams here. Okay, there is the mass. So I'll say this is 5 divided by 56 to get the number of moles and work it out from there. Divided by 56. The answer is 0,089. So this is 0,089 moles. Okay? From here, I can then go to the equation or the formula for concentration. Concentration equals number of moles. What's going on here? All right. Number of moles over volume. And that will be equal to number of moles is 0,089. 0,089 divided by 0,5. That is the volume. Okay? You get to that point. Don't worry yourself. You go to the calculator. I should have not erased that. 0,89 divided by 0,5. Okay? I should have just kept it there. Right. That is 1,78. That's going to be 1,78. So 1,78 mole per cubic decimeter. So that becomes the concentration. Okay. There we go. Let me see. I think there's something wrong here. Let me work, because here we made a mistake. That must be 0,089 divided by that. So let's go back to the calculator again quickly and we fix that. So instead of 0,89 is 0,089. We divide that by 0,5. And what do we get? We're getting it to be 0,178. So the answer is 0,178. Right. 0,178. 0,178. So that's 0,18, of course, mole per cubic decimeter. So we have found the concentration here, and therefore we have answered this question here. But a quick way of doing it, okay, without following all this, I'm trying to do that so that even those that are struggling can follow it up and get to the end, can find the logic in it. But then another quick way of doing it is to say, if I have got concentration, let me use a different color here. If I've got concentration as number of moles, if I have concentration as number of moles over volume, and yet number of moles in this case is mass over molar mass. If I put these two equations together so that I have C equals this N here, concentration, this N here is the M over M all over volume, okay, if you like. So what you have here finally is M over M divided by volume over 1. So that is, or can be written as M over capital letter M times 1 over volume. Therefore, at the end, you would find yourself having this. Let's work it out. You'll find having C equals M over MV. Right? And therefore, you can quickly substitute there, where you say, okay, that was 5 grams divided by this is 56 times the volume is 0.5. It was 500 cubic centimeters, so it's 0.5. So you can see that should work out to exactly the same answer that we got. Okay, so what you have there, you've got 5 divided by 56 times 0.5. Okay, what do you get? That is, there is your 0.178 or 0.179. Okay, it's actually the same. So this is 0.179. So just because I didn't get all the decimal points together, but you can see that works out to exactly the way it should be. So in other words, once you get used to these things, you can quickly apply that method. Once you have your molar mass and you've got the mass given to you and you are to get the concentration, the volume given to you in that equation or in that question, you can use that formula to work it out quickly.
I think it's time for a break now. Don't go away. We'll be right back. Welcome back from the break. Let's not waste any time and get straight back to today's revision lesson. Over to you.
I'm going to go straight now to our section that talks to improving your skills. Let's see how you are supposed to approach some of these questions here. Question number 1 says 8.4 cubic decimeters of nitrogen reacts completely. Oh, that's a key word. From what we have been talking about, you should be thinking twice about that word there. It reacts completely with hydrogen to produce ammonia at STP. All right, so this is at standard temperature and pressure. We know what happens there. We know what that condition is about. Question number A. Which substance is the limiting reactant? The limiting reactant is that substance that is used completely in a chemical reaction. And because it is used completely, this other one do not have any other thing to react with. So it has limited the reaction. It caused the reaction to stop there and then because it was no more. All of it was gone. So we, in our question here, we are told that nitrogen reacted completely. So because it reacted completely, nitrogen is our limiting reactant or limiting reagent. Okay, number B says write down a balanced chemical equation for this reaction. We know and we are told that this is nitrogen reacting with hydrogen. We know these are gases. The result is ammonia. Ammonia is NH3. Balance the equation. You would see here that we have got two nitrogen atoms, we only have one there, and for that reason we will put a 2 here, so that we have got a balanced number of nitrogen atoms left to right. But by putting this 2 here, we have done something to the hydrogen that is there. It is now 2 times 3. We have got 6 hydrogens on the right, so we need to make it 6 on the left as well. For us to do that, we need to put a 3 here, so that 3 times 2 gives us the 6. So the chemical equation is balanced in that way. All right. Now, moving on to question number C, we are asked to calculate the mass of ammonia produced in this reaction. Now, for us to calculate for the mass of ammonia produced, we will need to know how much of ammonia was produced in terms of moles. That is going to help us find the answer to this question. For us to do that, we go back to what is given to us. We are told that we've got 8,4 cubic decimeters of nitrogen. And this reaction occurs under STP. Now, it means I can calculate for the number of moles of nitrogen. Okay? And nitrogen, remember, is the limiting factor. So if I calculate for the number of moles of nitrogen, in this case, because it's standard temperature and pressure, I would use this formula here that says number of moles equals to given volume divided by molar volume. Okay, why am I doing that? Because I'm given the volume of nitrogen. So I can actually work out the number of moles in that volume of nitrogen. So number of moles of nitrogen in this volume will be equal to 8, what? Let's see what it is up there. It's 8,4 cubic decimeters. 8,4 divided by the molar volume at STP of a gas, 22,4. And how do we get the answer there? Here is our calculator. We've got 8,4 dividing that by 22,4. And what's the answer? Okay, we've got 0,375 moles. 0,375 moles of nitrogen. Now, all these moles of nitrogen have been used up. If it has been used up, according to our equation here, or chemical equation here, for every 1 mole of nitrogen, 2 moles of ammonia will be formed. So if the number of moles that have been used for nitrogen, okay, it's 0.375. The number of moles of ammonia that will be produced will be twice the number of moles of nitrogen that has been used, because this one tells us that for every 1 mole of nitrogen used, I'm going to have 2 moles of ammonia formed. So I can say that number of moles of ammonia formed or produced, this will be equal to twice the nitrogen moles used. I'm writing so that you see or you understand where all this comes from. Okay, 0,375, and that will be equal to, what is 0,375 times 2? Just multiply that by 2 and we get what it is, 0,75 moles. Okay, so 0,75 moles. 0,75 moles of ammonia have been formed. Now the question wants us to find the mass, not the number of moles. But for us to find the mass, we will then need the molar mass of ammonia, and I'll show you why later on. Now, molar mass of ammonia, okay, molar mass of ammonia, right? It's fine. Don't have my periodic table here with me, but let me see. It's 14 for nitrogen plus 3 into 1 for, so it's 14 for nitrogen plus 3 into 1 for hydrogen. So this works out to be 17 grams per mole. Okay, that is the molar mass. Why am I doing this? Okay, why am I doing this? I'm doing this because I have to use a formula now that would push me or would want me to use the molar mass to find the mass. Which one is that? If you remember well what it is, it says number of moles equals to given mass over molar mass. Okay, and from here then I can say that this number of moles for ammonia, remember I want the mass of ammonia. Number of moles for ammonia, it's this one here, 0.75. So I can say 0.75 then equals mass divided by the molar mass, which is 17. All right, and from here we can see that mass will be equal to 0.75 times 17. Let's see what we get here. So we can just take our answer here and times 17. And what do we get? 12.75 grams. So the mass of ammonia produced is 12.75 grams. Okay, so we have answered this question here, the question on calculating the mass. Okay, now coming to question number 2. All right, calculate the percentage water of crystallization in copper sulfate. The formula of crystallized copper sulfate is CuSO4 5H2O. All right, for us to find the percentage of water of crystallization, and remember that water of crystallization, we have to take that whole part there. All right, we again start by finding the molar mass of copper sulfate 5 waters. So we have waters in science here. Now how do we find that? Cu 63.5 plus S is 32 plus oxygen 4 into 16 plus water, I know it's 18 when you work it out, so let me just say 5 into 18 there. All right, so please check your periodic tables to find all the values that I'm putting in there. They are from the periodic table. Okay, just don't have it to display it for you here, so we see all those. When you work this one out, you should be able to get, let's see here, can do this here, say 18 times 5, okay, that's 90, so 4 times 16 is 64 plus 90 plus 32 plus 63.5. What do we get? 249.5. So we've got 249.5. 249.5 grams per mole. Okay? When we have that, we can find the water, the percentage water of crystallization, which will then be what? Percentage water of crystallization will be equal to 90 divided by 249.5 times 100. And that will work out to be, let's just check on it here. So it's 90. Okay, so this is 90 divided by 249.5 times 100. And what do we get? 36.1%. 36.07. So 36.07%. That is the percentage water of crystallization in hydrated copper sulfate. Okay, now coming to this one here. It says the percentage composition by mass for a compound is given below. Determine its empirical formula. You see here you've got potassium, there, and there. So you've got potassium, you've got chlorine, you've got oxygen. So for potassium, it will be 32/39. All right, this is potassium. And for chlorine, it's going to be what we have there, 29 over, this must be, what is this one here? Chlorine. Don't have my periodic table with me here. This should be 30, is it 31.5? Let me not even take a chance here. Don't want to mess up, but I'll show you how it works out to be at the end. All right, just don't have my periodic table with me quickly. So this will be for your chlorine. Okay, so let me just do that. We'll get it later on. Chlorine. And then for oxygen, it's 39/16. Okay, and that is oxygen. Right? You work out all these values here. Making use of your calculator. Let's just get these other ones here. 32/39 gives us 0.82. So this one is 0.82 for potassium. I know that this one is also going to work out as 0.82 because I worked out the solution. All right. And the last one, let's just get it quickly from the calculator. It's going to be 39 divided by 16. All right. And what do we get? That works out to be 2.44. So this is 2.44 for oxygen. Now, for us to find the empirical formula, you divide or you simplify. Okay, to do that, you divide by the smallest ratio, the smallest value in your ratio. Okay, and what is the smallest value? The smallest value here is the 0.82. So if you divide by 0.82 throughout, uh, 0.82 with there, you're going to get a ratio that says 1:1:2. Let's just work out 2.44 divided by 0.82 divided by 0.82. What do we get? We get 2.93. Now remember, with empirical formulas, the values we're getting here, we need to simplify them in such a way that we don't have commas at all. So 2.9 is basically 3. So we'll write that as 3 here. And what will then be the empirical formula here? The empirical formula is going to be, remember this is for potassium, K, and 1, so it's K1. The next one is chlorine, so it's Cl1, and the next one is oxygen. Oxygen is 3. So that is the empirical formula of the substance we were talking about here. Now look at it. This is potassium chlorate, okay? And as it is, it's actually giving us both the empirical formula and the molecular formula. So what we need to know is that with the empirical formula can give us the molecular formula, but the molecular formula is not necessarily the empirical formula. So in this case, we were lucky to find the empirical formula, and that formula happens to be the final formula for the substance that we were looking at.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to get the notes and to watch the videos from the term. Goodbye.